Okay, good morning all of you. I see only 42 students in the class. Anyway, we cannot wait. We need to get started, okay? Any questions from yesterday's class? Okay, let me recap what we are doing or what we did in yesterday's class. So, for this kind of section, which is shown in the first figure, we calculated cracking moment. MCR is equal to FCR IT divided by YT. So that we calculated, assuming the transformed area or the steel area contribution is neglecting the steel area contribution as well as including the steel area contribution. We calculated what is MCR. MCR is nothing but cracking moment. The idea of calculating this cracking moment is to check whether for a given applied moment, whether a beam is what kind of cross section, transformed cross section we need to consider. Okay, so yesterday we went through all this exercise, and then at the end we also calculated stresses in concrete at the top fiber as well as at the bottom fiber. Top fiber is in compression, bottom fiber is in tension. So that this is what we calculated FC, and also let me put it in a like this mode. FC, compressive stress in concrete in the extreme fiber, and also tensile stress in concrete in the extreme fiber, the bottom fiber, F tilde CT. And also we calculated the stress in steel using this transformed stress, the stress distribution for transformed section. Once you know FCS, FCS is nothing but stress in concrete at the level of steel, and using that you can calculate what is the stress in steel. Okay, stress in concrete at the level of steel. Once you know that, you can calculate stress in steel. So this is what we did yesterday. Any questions here? So basically what we did is, given a section, all the geometrical details, all the geometric dimensions as well as the steel that is provided, what we did is we analyzed it. We analyzed and then got the stresses. So this is like given a section, how to do analysis. Okay, there are two types, it can be analysis or it can be design. So whatever we are doing currently is analysis of a given reinforced concrete section. Based on that, what is its cracking moment and what are the stresses in the steel as well as concrete. Okay, any questions here?
Okay, let me just add some comment. See, the working stress method is typically used for serviceability checks. Now, this particular problem gives the essence that under service condition, whether a section will crack or not. This has an implication in durability checks. When we will be studying the crack width, again, we will revisit this exercise that if it cracks, then only there is a meaning of finding out crack width. Similarly, what are the stresses in the concrete and steel? That is also of importance under service condition. Okay.
And for completeness, whatever Professor Amlan just mentioned, let me go and show you section C, we already looked at this earlier in the earlier classes. I showed you about this effective moment of inertia. Let me magnify this effective moment of inertia. Let's go and see once again this one. Effective moment of inertia is given by this formula, okay? And where IR is moment of inertia of cracked section. So now you can appreciate what exactly this means, okay? Assuming the concrete below the neutral axis is ineffective. So whatever moment of inertia of the transformed section, that is this IR. IR is moment of inertia of cracked section, and whatever we denoted MCR in the lecture we just covered, that here it is denoted as MR. MR is nothing but cracking moment, and it is calculated. Here it is calculated as FCR multiplied by IGR divided by YT. Here MR is the cracking moment, assuming the entire cross section is effective. So that's why gross moment of inertia is used here. So that is what this MR based on FCR. FCR is nothing but modulus of this one rupture for concrete. Okay. So now you can understand what is this MR. It's nothing but cracking moment. Just now whatever we calculated, similar to that. And then once you get an idea about MR, okay, and then you can make use of this equation. You can make use of this equation. I effective is IR. IR is moment of inertia of cracked section. And everything is self-explanatory here. In the denominator, 1.2 is some numerical value. MR is cracking moment. M is the actual moment that is applied, and Z is the lever arm. We will see what it is. What is this lever arm? We will see in today's class. Okay, and D is the effective depth. Effective depth is overall depth minus the cover thickness, that is effective depth, and 1 minus X over D. X is neutral axis, depth of neutral axis. X is depth of neutral axis. And BW is actually this formula. Please note that whatever formula that is given here for I effective, that is more general. So that's why BW is used. It's width of the or breadth of the web to denote that it is related to web section or web portion of section. It is written as BW. And B is the breadth of the compression phase. Actually, this formula is written for a more general case of a flanged section. A rectangular section can be assumed as a flanged section where BW is same as B. Okay, so now you can see where this cracking moment is used, and basically whatever just now whatever Professor Amlan mentioned. For serviceability limit state, deflection is one of the serviceability limit state. There will be using all this cracking moment and other things. Okay. Once again, we'll come back to this at a later stage. So let me. So now in today's class, we'll continue where we left yesterday. So yesterday we calculated cracking moment and also stresses in steel as well as in concrete. Before I proceed further, please note that whatever we are doing, it is based on working stress method. So we'll learn few concepts related to this method, then we'll switch over to limit state method. Okay, so that is what is written here. Analysis of reinforced concrete RCC beam using working stress method. So before I proceed further for today's class, let me go and show you what we noted as a part of design approaches. Please see, I explained to you earlier as well about these design approaches. The first approach is this working stress method. In working stress method, let's see what are the various important points related to this method. Factor of safety applied to the yield or ultimate stress to get the permissible stress. So the actual value of yield stress or ultimate stress on that factor of safety is applied and permissible stresses are obtained. Okay. Structure is designed to support working or service loads without exceeding the permissible stresses in concrete and steel. So we are going to design the structure such a way that the loads or whatever working loads or service loads, because of that whatever stresses that are coming in concrete and steel, they are not exceeding the permissible values. Okay. So these are the two important points that we need to keep in mind related to this working stress method. So now let's see where these permissible, who is going to give us these permissible stresses in concrete and permissible stresses in steel. And please note that once again, I want to emphasize that all of you should have this code book with you when the lecture is going on. Otherwise, it's very difficult to follow. So now let's, just now we noted the two important points related to working stress method. So let's note down few more points. So we are focusing on this annexure B of IS 456-2000. So let's see this one, assumptions for design of members. Okay. In the methods based on elastic theory, this working stress method is based on that. Okay. The following assumptions shall be made. At any cross sections, plane sections before bending remain plane after bending. Actually, this whether it is working stress method or limit state method, this assumption is going to be there. The implication of this method is strain distribution is linear across the depth of the section. And this is valid only when there is a perfect bond. Please note that this is valid only when there is a perfect bond between steel and concrete. Okay. And next point is all the tensile stresses are taken up by reinforcement, none by concrete, except as otherwise specifically permitted. Okay. All the tensile stresses are taken up by the reinforcement, none by the concrete, except as otherwise specifically permitted. Okay. So this is the second assumption. And the third one is stress-strain relationship of steel and concrete under working loads is a straight line. That means we are assuming, we noted what is stress-strain curve for concrete and stress-strain curve for steel. And in working stress method, we are actually making use of only that portion of the curve or that portion of stress-strain curve which is linear. Stress-strain relationship of steel and concrete under working loads is straight line. So that is another important assumption. Okay. So this is where your this stress distribution diagram is going to change between working stress and limit state. At that point, when we come to the limit state, I will once again show you that. Okay. So this is the third point. Stress-strain relationship is linear. And modular ratio, we already noted it is 280 divided by sigma CBC. Okay. So now let's see this one. Permissible stresses in permissible stresses. Under that you have permissible stresses in concrete as well as permissible stresses in steel reinforcement. So table 21 is giving you Table 21 is giving you permissible stresses in concrete. For different grades of concrete, what are the permissible stresses? And please note that what we noted in the one of the point related to working stress method, some factor of safety is applied on yield stress or ultimate stress, and permissible stress values are obtained. So code is recommending to use these ones. Okay. Permissible stress in compression under bending and under direct, and permissible stress for bond. We'll see when the time comes related to this third column as well as the fourth column. This permissible stress in compression direct, this column, and this we'll see at a later stage. Now we are focusing on flexural members. So compression is going to happen because of bending. So permissible stress in concrete, depending on the grade of concrete, these are the permissible stress values. Second column, okay? And now, what about, so that is what is mentioned here. Permissible stresses for various grades of concrete shall be taken as those given in table 21 and 23. 23, we'll see what it is. This is related to shear. When we come to the shear reinforcement design, then we'll look at this one. Okay, table 23. Since we are now focusing only the flexural or the issues related with flexural analysis, so let's focus only on table 21. Table 21 is giving you permissible stresses in concrete under bending and as well as in compression. Okay. So, and now what about permissible stresses in steel? Permissible stresses in steel reinforcement shall not exceed values specified in table 22. So, table 22 is giving you for different types of steel, what should be the permissible value that we need to use under different situations. In the sense, if there is only tension, you can see here. First, let's read this table carefully. Permissible stresses in steel reinforcement. Okay. Type of stress in steel reinforcement and tension. And it is here, if you see sigma ST or sigma SV. SV is related to shear, we'll see later. Okay. So, sigma ST means to indicate that steel is in tension, sigma ST is used. So, under tension, depending on the diameter of the bar, if it is mild steel, what is the permissible stress value that is given here? And if it is medium tensile steel, it is giving a guideline. Half the guaranteed yield stress subjected to a maximum of 190. Please note that whatever numbers that are given here, 140, 130, all these numbers, Newton per mm square, permissible stresses in Newton per mm square. Okay. So, and what about Hysd? High yield strength deformed bars conforming to IS 1786. That is nothing but grade FE415. For that, what is the permissible stress value in tension depending on the diameter of the bar? If it is less than 20 mm, what is the value? If it is greater than 20 mm, what is the value? Okay. And similarly, if the reinforcement is in compression in a column, okay, sigma SC is for steel to emphasize that it is in compression. C is used. C is used, so it is sigma SC. Compression in column bars. What is the permissible stress value that is given here? And compression in bars in a slab. Anyway, the description is given here. Whenever we require, depending on the situation, we need to go to this table and check the corresponding permissible value we need to take. Okay. So now you can also read this for the FE415 only up to FE415. These columns are given. What about higher grades? Some information how to handle those things they are given here. Okay. For high yield strength deformed bars of FE500, grade FE500, the permissible stress in direct tension and in flexural tension shall be 0.55 Fy. The permissible stresses for shear and compression reinforcement shall be as per grade FE415. Okay. So this is how these permissible stress values are specified in the code. So we need to make sure our permissible values are not exceeding these things. Okay. And we'll be using these permissible values, and we'll be designing the sections using this working stress method. Any questions here? So now let's start with this. Please make a note of this section. Reinforced concrete rectangular section. Steel is provided in the tension side. Assuming the beam is subjected to sagging moment, steel is provided on the tension side. Please make a note of this figure. Width of this section is B. Please note that I'm taking some of these materials from different sources. So notation may be slightly different. So you need to pay attention and take a note of the corresponding points. Okay. So width of the section is B, and effective depth is D. Effective depth is from the top edge or the fiber, extreme fiber, which is in compression, from that to the CG of the reinforcement, center of gravity of the reinforcement. And before that, before this, I want to show you one more thing. These permissible stresses in steel reinforcement are given in table 22. Okay, where exactly? Suppose if I provide steel, in different 2 or 3 layers, where this value, the permissible stress value, I need to make sure the stress is not exceeding that. So that information is given here in this section. Okay, let's see that. In flexural members, the value of sigma st given in table 22 is applicable at the centroid of the tensile reinforcement. Okay, so if you have one layer of steel, then it should be at the centroid, subject to the condition that when more than one layer of tensile reinforcement is provided, the stress at the centroid of the outermost layer shall not exceed more than 10% the value given in table 22. Anyway, we need to make make a note of the centroid of the reinforcement. Okay, centroid of the reinforcement. If you are providing steel in different layers, or if you are providing steel in one layer also, CG of the reinforcement, we need to keep a note. So now coming back to this one, effective depth is to the centroid of the reinforcement. Is this clear? First figure, and second figure is based on whatever things that we noted in last classes. Transformed section. Assuming the concrete below the neutral axis is ineffective. Please see the notation here. Again, width of the section is B, and the neutral axis depth. Neutral axis depth is denoted with N. Please make a note of it. N, small n is used to denote the neutral axis depth. N is equal to KD. D is the effective depth. K is nothing but neutral axis depth factor. Neutral axis depth factor K, small k. So N can be written as some factor multiplied by effective depth. Okay. So what is the significance of this K? We will see in a while. Okay. Neutral axis depth factor K. N is equal to KD. And if this is N, and what is the rest? What is the remaining portion? Remaining portion is going to be D minus N. Or you can write it as D minus KD. Or you can write it as D multiplied by 1 minus K. And this is nothing but your equivalent area of concrete. And please note that we are considering a case where concrete is ineffective below the neutral axis. So M minus 1 is not there here, because only steel is taking care. So M multiplied by AST. Is this clear? Transformed section. And please note that steel is in tension, that's why M. And now strain distribution. Strain, plane sections remain plane before and after bending. So strain variation is going to be linear. And till yesterday, in the yesterday's lecture, we are writing everything in terms of epsilon. Here it is written in terms of sigma. Okay, strain in the extreme fiber. Strain in the extreme fiber is actually stress in the extreme fiber divided by modulus of elasticity of concrete. Okay, sigma prime CBC. Sigma prime CBC is nothing but what is the compressive stress in concrete in the extreme fiber, and EC is the Young's modulus of concrete. And strain variation is linear. Strain variation is linear. Strain at the level of steel is going to be stress in steel, which is sigma prime ST divided by Young's modulus of steel. Please note that we are assuming perfect bond between steel and concrete. We are assuming perfect bond between steel and concrete. What is the meaning of that? Strain in concrete is going to be same as strain in steel. Okay? Any questions in the strain diagram? Any questions in this related to strain diagram? And now, in the working stress method, we noted the third assumption is stress-strain relationship is linear. So you got the strain distribution, you got the strain value, so corresponding stress value you can easily find. So the stress distribution is going to be looking like this. So how do you get from strain? How do you get stress? You multiply whatever strain value, you multiply with corresponding modulus of elasticity, and here in the top portion it's going to be modulus of elasticity of concrete. So sigma CBC prime divided by EC multiplied by EC is going to give you stress distribution. This portion. Strain is 0 here, so stress is going to be 0 here. Strain here is sigma CBC prime, CBC divided by EC. So multiply with EC, you are going to get sigma prime CBC. And in between, it's going to be linear. Stress distribution is going to be linear. Okay? And you can see here this stress distribution is looking like a triangle. This is a triangular distribution, or it's having triangular shape. And if you want to find CG of this triangle, it's going to be at from the base for a triangle. Centroid is going to be at a distance 1/3 distance from the base of the triangle. So taking base on the top edge as the base of triangle, this CG or the centroid of this stress distribution in concrete is going to be lying at a distance. Neutral axis is denoted with n, so this distance is going to be 1/3 of that. So this distance is n divided by 3. And now coming to this strain in steel. Strain in steel is sigma prime ST divided by ES. Please note that here in the stress diagram, whatever we plotted or whatever we have shown is in terms of concrete. So, and if I want, this is the stress distribution or stress diagram for transformed section. Transformed section is in terms of concrete. So stress here, in at the level of steel, stress is going to be sigma prime ST divided by M. And you go back to yesterday's whatever lecture or in the last classes whatever we covered. F2 is equal to F1 times M, or F1 is equal to F2 divided by M. F1 is nothing but stress in concrete, F2 is nothing but stress in steel. So using that, the stress in steel or stress in concrete at the level of steel is sigma prime ST divided by M. Is it clear? What is this M? What is this M? Modular ratio. How is it defined? Modulus of elasticity of steel to modulus of elasticity of concrete. Okay? And what about, so this is the stress in steel. This is the stress in steel. So what is the total tension or total force in the steel? Stress in steel multiplied by the area of steel, area of the transformed section. So sigma prime ST divided by M multiplied by M AST. So that's going to give you AST multiplied by sigma prime ST. And please note that this this portion is the steel is in the tension side, so T is used. So total tensile force is AST multiplied by sigma prime ST. And what about total compressive force? This stress distribution, this triangular stress distribution is acting over this area. So what is the total compressive force? Total compressive force is obtained by B times N is the area on which this compressive stress is acting, and this compressive stress is varying from 0 to some value here, sigma CBC prime over sigma CBC prime. So stress is varying from 0 to sigma CBC, linearly varying. So total compression is going to be area under compression, and since this is linearly varying stress, half is coming, half the maximum value, half of sigma CBC prime. So that is total compression. Total compression is half sigma CBC prime multiplied by B times N. And where this, whenever you say force, we need to say, or we need to indicate at what location this force is going to act. So this C is going to act at this centroid of this triangle. That centroid of the triangle, we noted it is N divided by 3. So C is going to act at a distance from the top edge. Below the top edge, it's going to act at a distance N divided by 3. And what is the distance between C and N? C and T. T is going to act at the centroid of the reinforcement, and C is going to act at this level. So the difference or the distance between these two, once you know this value, the effective depth is D minus N divided by 3 is going to be the distance between C and T. And that distance is called lever arm distance. That distance is called lever arm distance. That is denoted with this JD. Okay, and why JD? You can write this D minus N over 3. N you can write it as KD. N you can write it as KD. Okay. Then what this lever arm distance is going to become? D multiplied by 1 minus K divided by 3. Okay, this lever arm distance is going to be D multiplied by, in brackets, 1 minus K divided by 3. That 1 minus K divided by 3 is nothing but your J. J is called lever arm factor. J is called lever arm factor. Hope you are noting down in your notes. J is called lever arm factor. K is called neutral axis depth factor. Okay. Any questions here? Professor Amlan, you want to add something here? Because this is very, very important, all these notations, everything.
Okay, let me just add a few sentences for clarity. In this type of analysis problems, what we are doing is that from the original section, we are going to the transform section. And then first we are drawing the strain diagram. In the strain diagram, we are following one important principle which is called strain compatibility. What is the strain compatibility? The strain in the concrete in the vicinity of the steel is same as the strain in the steel. Now from the strain diagram, we are going to the stress diagram. Now while drawing the stress diagram, we are invoking the principle of constitutive models. Under the working stress, both the materials are considered to have linear stress versus strain. Now from the stress diagram, we are going to the forces. And next you will see that we will write the equilibrium equations in terms of these forces. These are the steps I would suggest that please follow, that from the section, you draw the strain diagram. From the strain diagram, you draw the stress diagram. And from the stress diagram, you go to the forces. And then you will be able to write these equations very neatly. You don't have to memorize anything. These are all based on nice mechanics, and you should be able to write them. The similar approach we will also take during the limit states method, which we will discuss later.
Students, any questions? So everything is clear here. So you have this section. This is the transform section. Assuming concrete is ineffective below the neutral axis, strain diagram. From that you get the stress diagram. And from stress diagram you get this resultant compressive force, resultant tensile force. And what is the distance between resultant compressive force, resultant tensile force. Everything is clear. So if everything is clear, let me proceed further. So let's, whatever I explained to you, that is again reproduced here, that figure. So now we need to find the neutral axis depth, n value. N is the neutral axis depth. So how do we get the neutral axis depth? So you need to take the area in compression. Moment of area in compression is equated to moment in area in tension. What is the area which is in compression? B times N. And what is the moment of that area with respect to the neutral axis? Area multiplied by the distance from the centroid of that particular area to the neutral axis. So that distance is N divided by 2. So that is what this equation is. Okay. So this first portion is nothing but this side of the equation is nothing but moment of the area in compression with respect to the neutral axis. And what about moment of area in tension with respect to the neutral axis? Moment of area. First of all, what is the area in compression? Area in tension. What is the area in tension? M times AST is the area in tension. And what is the distance of centroid of that area from the neutral axis? D minus M. So M AST multiplied by D minus M. So moment of area in compression with respect to the neutral axis is equated to moment of area in tension with respect to the neutral axis. So you got a quadratic equation. Here you can see B is the width of the section, you know that. 2 is a numerical value. M is modular ratio, which depends on grade of concrete. Okay. So you can easily get M value using that relation 280 divided by 3 times sigma CBC. And AST section is given to you, so you know what is the area of steel. And D effective depth section is given, so you know what is D. Except N, you know everything in this equation. and this is going to be a quadratic equation M. You need to solve the quadratic equation and then get the realistic roots. That gives you an idea about the neutral axis depth N. Okay, that gives you an idea about neutral axis depth N. Now this equation can be written in a different way. That is what is given here. Usually area of steel we are going to specify. Suppose in some cases area of steel may be specified as a percentage of the cross section dimensions. Okay, so if the area of steel is specified like that, that is a P percent of the cross sectional area. So P times BD. AST is written as P times BD. P is nothing but the percentage of steel with respect to the total cross-sectional area. Okay.
Can I just interrupt? Please note that the percentage is defined based on what I would say the effective cross-sectional area. The area of the steel divided by the width and the effective depth. See, sometimes students get confused. Do not use the total depth. In flexural calculations, after cracking, it is the effective depth which makes more sense because we write all our equilibrium equations based on the effective depth. Hence, the percentage is also based on the effective depth, which is denoted as small d.
Okay, this effective depth, anyway, this percentage of steel is with respect to the effective depth. Okay, so P is defined like this. P is area of area of steel divided by the cross section taking effective depth. Okay, cross section of the this beam taking effective depth. And now if AST is defined like this, then this equation can be rewritten in this manner in terms of P. In terms of P, this quadratic equation can be rewritten like this, and you can go back to your basics, high school mathematics, and try to find what are the roots of this equation, and take the realistic root, and then you find the neutral axis there. Okay, ax square plus bx plus c, something like that. You can see. You can make use of that formula which you have studied in your high school, and they take the realistic root. That is what is written here. So that equating the neutral axis, n is equal to that realistic root. You get this equation, and this equation we define just when I am explaining earlier. N is equal to, N is written as some factor times the effective depth. K factor is defined, neutral axis depth factor. So once you get N, you can write neutral axis depth factor like this. So neutral axis depth factor in terms of percentage of steel and modular ratio. So you can see here this equation. What is the significance of this equation? Neutral axis depth factor. Neutral axis depth factor is dependent on the modular ratio as well as the percentage of steel that you provided. So if you know the grade of concrete and if you know the percentage of steel that you provided, you can easily find what is the neutral axis depth factor. So it's not actually going to depend, or once you get this neutral axis depth factor, irrespective of whatever effective depth of a particular beam is there, you can easily find what is the neutral axis depth, which is going to be a function of only the modular ratio and the percentage of steel. Okay, so you can prepare a table. You can prepare a table with different grades of concrete and different percentage of steels. What is the neutral axis depth factor? Any questions here about this neutral axis depth factor? And once you get the neutral axis depth, you can go to your whatever equations we noted or whatever the tensile, resultant tensile force, resultant compressive force, we can easily find what is this. What is this resultant compressive force C? What is this resultant tensile force T? So resultant tensile force, straightforward, area of steel times stress in steel, and resultant compressive force is half sigma prime CBC B times N. Just now we noted that we can calculate neutral axis depth using this equation. So you can plug in that here. So you get the total or the resultant compressive force. And what about lever arm factor? Lever arm factor or lever arm distance? Lever arm distance is given by this one. Lever arm is J times D. That can be written as D minus N divided by 3. And that I already mentioned to you. This can be rewritten in this manner. And once you get the neutral axis depth factor, you can calculate this lever arm. Or once you get neutral axis depth factor, you can prepare another like a column in that particular table showing the lever arm factor. Lever arm factor is 1 minus K divided by 3. Any questions?
Okay, let me just add a few comments. So you may think that why are we introducing this type of factors? See, these factors are actually dimensionless numbers. See, the theory is such that whether you are using the SI system of units in India or whether you use the US systems, it doesn't matter. If I'm using dimensionless numbers, this expression of K is unit independent. It is expressed in terms of, again, two dimensionless numbers. Percentage of steel is dimensionless and the modulus ratio is also dimensionless. Hence, this type of equations are valid for any type of system of units that you use. Okay.
Okay. So now, please note that this resultant compressive force C has to balance resultant tensile force T. Okay. Because otherwise section is not going to be in equilibrium. Resultant compressive force C should be equal to resultant tensile force T. So if that is the case, this is C resultant compressive force and resultant tensile force separated by this distance lever arm. They are going to form a couple that is going to be same as whatever moment that you apply. Okay. So that we already noted. So M is equal to moment, the moment that is applied is equal to T times lever arm or C times lever arm. Okay. So let's make a note of it. So the moment that is applied moment M is equal to T times lever arm, which is JD, or C times lever arm. And if you have this relation, M is equal to T times JD or C times JD, you can easily find what are the stresses given a particular moment. What are the stresses that are developed in the steel? You can back calculate. What is the extreme fiber stress in compression in concrete? That also you can find. Okay. T is equal to, here T is equal to AST multiplied by sigma prime ST. If you rearrange it, you are going to get this one. And C is equal to half sigma CBC prime multiplied by B times N. So if you substitute that C value here and rearrange it, you can write sigma CBC prime like this. So make a note of these two equations. Sigma ST prime, sigma CBC prime. You make a note of these two equations. Once you know the lever arm distance and once you know the cross-sectional details and applied moment, you can easily find stress in steel and stress in concrete.
See, let me just add one comment here. See, one important concept in this working stress method is the use of linear elastic material models. Now, if we do that, then the neutral axis, the depth of the neutral axis is same as the depth of the centroid of the section. This can be proved by the first equilibrium equation, which states compression should be equal to tension. Please check in your mechanics of materials book that the depth of the neutral axis for a linear elastic analysis is same as the depth of the centroid. This will not be used in the limit states method, which we'll be studying subsequently. And another important thing you will be noting here, that the stresses, expression of stresses, what we are seeing today, they can also be found out using the moment of inertia of the cracked section. See, yesterday we found out the stresses for a moment which was less than the cracking moment, and hence we use the moment of inertia of the gross section. But once the moment exceeds the cracking moment, then we have to use the moment of inertia of the cracked section. Please note the difference. Okay.
Okay, in continuation with what Professor Amlan just mentioned, you can calculate stresses in steel and concrete using this equation, which is coming from simple theory of simple bending. M is equal to Fz, or that kind of thing. Okay, so using this equation, you can calculate sigma, the stress in steel as well as stress in concrete, or you can make use of whatever concepts we learned yesterday. You can make use of the moment of inertia of the transformed section, cracked. Here we are assuming concrete below the neutral axis is ineffective. So for this kind of transformed section, you can find the moment of inertia about the neutral axis. So that is what is written here, which is self-explanatory. Let's go through this quickly. For this section, cracked section, what is the moment of inertia? Moment of inertia of this portion. Moment of inertia of this rectangle B times n, and we are taking moment of inertia about one of its edges. So it's going to be B times n multiplied by B times n cube divided by 3. So yesterday we noted this kind of formula. If you have a rectangle having dimensions B and D, and if you are taking a moment of inertia about one of the edges, it's going to be B D cube divided by 3. That formula is applied here for this portion. What about this portion? Yesterday we discussed this steel is at a distance from the neutral axis. The centroid of the steel is away from the neutral axis by a distance d minus n. So the contribution of this steel to the total moment of inertia is going to be moment of inertia of this steel about its own axis plus area of this steel, that is m times ast, multiplied by the distance of this centroid of this steel from the neutral axis, which is d minus n square. But yesterday we noted that, or Professor Amlan also mentioned, you can ignore the moment of inertia of steel about its own axis. If you do that, finally you get the moment of the steel contribution to the moment of inertia like this: m multiplied by ast multiplied by square of the distance from the centroid of the steel to the axis that you are looking at. The axis that you are looking at is this neutral axis at the distance d minus n. So d minus n square. So this is the moment of inertia of transformed section. So you can make use of it, and whatever the procedure that we followed. Once you get the cracked moment of inertia, a cracked section of this moment of inertia of cracked section, you can find the stress in concrete and stress in steel, following whatever approach we did yesterday. If you understood whatever we did yesterday, then you can follow that way as well to find the stresses in steel and concrete. Okay. And finally, I think we'll stop here. We'll stop here, and in tomorrow's class we'll continue further. But you please go through this entire material because this is very, very important. And if you have any questions, you please let us know. Any questions? Any questions?
Okay, I will add some comments in tomorrow's class at the beginning. Okay.
Just 1 second, 1 second. Okay, thank you.